Last time we were talking about complex numbers, right? Complex numbers, and we talked about the size of complex numbers, right? So you have some number, right? Some number can be represented by a point on the plane, right? Some combination of 1 and I, right? And we said that we can talk about the size of a complex number. The size of the complex number is 1/2 z times z bar. I'm sorry, the square root of z bar, which of course works out to be the square root of a squared plus b squared. So that's what you normally think of as the size of a vector, right? The size of a vector, or the size of the distance to the origin in the plane, right? Okay, so so since we have these things, we can actually talk about. So we can actually talk about power series of complex numbers. Okay, so you can consider functions of the form summation a sub n z to the n, right? From n equals 0 to infinity. Okay, just like we did for real numbers, we can do the same thing for complex numbers, right? Where a sub n are your coefficients, but we allow them to be complex numbers. Okay, and basically the things that we've been doing the last few weeks for real numbers, all of that holds for complex numbers. So for example, so similar, so analogous theorems hold. Analogous theorems hold. For example, the theorem that says that convergence at a point implies absolute convergence. So convergence of a power series centered at 0 at a point implies absolute convergence for all z of smaller size. Right, you remember that for the real numbers, right? When we were talking about real power series, it turned out that if you converged at some point, if your power series converged at some point, then you knew that it absolutely converged on the open interval from here to here, right? Remember that? Hope you remember that. Okay. The same sort of thing happens. In fact, the same proof happens, right? The same proof works. If a sub n z naught to the n converges, if that converges, then whenever the modulus of z is smaller than the modulus of z naught, we see that the sums of the absolute values equals the sum of a n z to the n over z naught to the n. Just like we did in the real version. I hope you remember we played this trick. We slid in the z naught. We slid in the z naught by dividing by z naught also. We multiplied by 1 as we do very often. Okay, and then, right, a n z naught to the n is going to go to 0. Because this converges, these guys go to 0, like by the divergence test, right? If a series converges, that means that the terms have to converge to 0. Right? That's still going to hold. Right? So these guys are going to go to 0, right? And so we can compare with summation z over z naught to the n, right? But that's a geometric series where the ratio is smaller than 1, right? Which is a convergent geometric series. Which is a convergent geometric series. Okay. In any case, the point is that exactly the same proof works, right? Exactly the same proof works. Okay, so what we get in the complex plane is this. If you converge at some point z naught, then you absolutely converge for every point of magnitude less than that of z naught, right? In other words, you have absolute convergence in this disk. Okay. And so the domains of convergence, for power series of complex numbers are disks, right? They're disks possibly with some points on the boundary. Okay, possibly with some points on the boundary. Just like for the real guys, you get intervals, possibly with points on the ends, right? Plus or minus points on the ends. Okay. Okay, everybody following? Okay. Okay, so so for example, if we look at summation z to the n over n factorial from n equals 0 to infinity. Okay, that thing, remember, is the power series for e to the x, right? That's the power series for e to the x. That's the power series for e to the x, right? Which we know converges on the whole line, the whole real line, right? Okay. It converges on the whole real line, right? So what does that tell you about the power series, the convergence, the domain of convergence of this guy? It has to be a disk, right? It has to be right? We know it converges here, so it converges on this disk, absolutely. It converges here, so it converges on this disk, absolutely, right? And so on and so forth. This actually converges on the whole complex plane, right? Converges on all of C, right? Absolutely converges, in fact. Converges on all of C. Okay. Similarly, sine, if we look at negative 1 to the n plus 1, z to the 2n plus 1 over 2n plus 1 factorial, or summation negative 1 to the n, z to the 2n over 2n plus 2n factorial. These guys also, these are the sort of generalizations of the sine x and cosine x series, right? And so these things are going to converge on all of C. Okay, now here's where things get cool. So this is how we talk about the cosine of an imaginary, of a complex number, right? This is how you define the cosine of a complex number, the sine or the cosine of a complex number, right? You say, well, I'm going to define sine of a complex number by using the power series expansion, right? And that will agree with your real valued real valued notion of sine and cosine. Even though sine and cosine now don't have anything, are not based on the unit circle or on triangles or something, right? You're talking about sine of a complex number. Okay, cosine of a complex number. Right. So right, this is how you generalize the notion of e to the x to complex numbers. Okay. So you find a power series expansion that agrees with your real power series expansion, and then extend it to and then notice that thing actually is valid on the whole plane. So let's just use that as our definition. Okay. Right. Similarly, a bit more complicated. If we look at natural log of 1 plus x, that's x minus x squared over 2 plus x cubed over 3 minus plus, etc. And that is actually valid on this interval here. Okay. That's valid between 0 and 2. Okay, that's valid between 0 and 2. I mean, that's how to say it. That's valid for x smaller than 1, right? That's valid for x. That has a convergence for x smaller than 1, which means that you can get the natural log between 0 and 2, right? Because x is smaller than 1, so we can get the natural log between 0 and 2. Okay. Okay, so you can extend natural log of 1 plus z, right? I mean z squared over 2 plus z cubed over 3, blah, blah, blah. So you just generalize. You can generalize the natural log. You can generalize the natural log to complex numbers, right? But you see that this is valid, so you can get natural log of z where the distance of z to 1 is smaller than 1, right? So inside here. Right. Okay, but it's a little bit different in this case because it's not valid on the whole line, right? It's only valid this is only valid where absolute value of z is less than 1. Okay, so we in some sense we can't you can't extend the natural log on the entire complex plane. Okay, so it's a little bit more complicated. 15 minutes. I think we can do it. Okay. So the other properties hold, right? They're like the rules about adding series, right? If I want the series for sine plus cosine, it's just going to be the sum of this. If I want to take the derivative of this, you just differentiate termwise. There's properties of complex. I'm sorry, the properties of power series still hold. So properties of power series also still hold. So, so for example, if I look at e to the iz, if I look at e to the iz, then that's going to be iz to the n over n factorial. And suppose I multiply a number by z. Okay. Well, what's that? If we work it out, right, you get iz to the 0 over 0 factorial, that's 1. Iz to the 1 over 1 factorial, plus iz squared, right, iz quantity squared over 2 factorial, plus iz cubed over 3 factorial, plus blah, 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 it should be one more, iz to the 4th over 4 factorial, etc., etc. Okay, of course. And if I pull out the i's, I get I times z over 1 factorial. Here I've got an I squared, well that's negative 1 times z squared over 2 factorial. Here I've got I cubed, that's negative I, z cubed over 3 factorial. Here I've got I to the 4th, that's just 1 again, so I get z to the 4th over 4 factorial, etc. Okay, and I'm gonna separate this into the terms that have an imaginary part on it, have an I on it, and the terms that don't have an I on it. Right, so I get 1 minus z squared over 2 factorial plus z 4th over 4 factorial plus minus, etc. And I also get I times z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus, etc. Okay, and maybe you see the joke, right? You see the funny thing that happens, right? The cute thing that happens. What is this thing here? This is This is something we've seen very recently. This is the cosine, right? This is the cosine. This is cosine of z. And this guy is a sine. Okay. So cosine and sine are very close relatives of the exponential function, even though it didn't seem like it, right? Sure didn't seem like it when you were introduced to them. Right. In fact, you could express cosine very cleanly as e to the iz plus e to the minus iz over 2. And sine as e to the iz minus e to the minus iz over 2i. As a consequence of this relation. This is a pretty famous formula. It's called, when I first saw it, pretty sure it was called de Moivre's formula, but I see most people call this Euler's formula. So maybe it's actually Euler who discovered it. I don't know. Sometimes you have formulas that are given the wrong names, right? And then they're corrected, or not corrected. Like there's something called the Cauchy-Schwarz inequality, and there'll always be some Russian who says, "You mean the Cauchy-Schwarz-Bunyakovsky inequality?" And they're like, "Okay, yeah." Okay, 9 minutes. Okay, so another thing that you can see from this is that one can get directly that e to the a times e to the b equals e to the a plus b. Okay, and the way you do it is just by multiplying. You use the fact that you can multiply power series as if they were polynomials, right? So using multiply like polynomials, using the fact that you can basically multiply power series like polynomials, well, you just say, I'm going to take 1 plus a squared over 2 factorial, blah, 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 times 1 plus b squared over 2 factorial plus blah, blah, blah. And then it works out to be 1 plus a plus b plus a squared plus 2ab plus b squared over 2 factorial plus blah, blah, blah. Which, anyway, maybe I didn't need to say this. I should probably just have left it at this. Okay. You can get this formula by multiplying. You can get this formula by multiplying the power series out. Okay. Let me just let's just go on because there's not much time. Okay, so a cool application of this stuff there's one cool application of this stuff to trigonometry. Suppose that theta 1 and theta 2 are real numbers. This will actually work even if they're complex numbers, but you have to be just a tad more careful. Okay, but let me just show it for real numbers for succinctness. Okay, so you say, okay, let's look at e to the theta 1 plus theta 2, e to the I theta 1 plus theta 2. Okay. By Euler's formula or de Moivre's formula, that's going to be cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Okay. Cool application of trigonometry, how all trig formulas arise and be obtained. The complex power series. Maybe not all of them, but a lot of them. Okay, so here we go. De Moivre's formula for a sum. De Moivre's formula for a sum. E to the I theta 1 plus theta 2 cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Okay? Now, you say, okay, but this is the same thing as e to the, using this fact, right? We can write this as a product, right? E to the I theta 1 plus e to the times e to the I theta 2. Okay? So, well, let's use de Moivre's formula again. Let me go back over here. Now let's go this way. So cosine theta 1, cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. Right? But what is that? That's cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, plus I times sine theta 1, cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. Right? Because, right, you get cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, right, from the i's multiply, you get a minus. Cosine theta 1, cosine A, cosine B, minus sine A, sine B, right? This should sound kind of familiar. Here you get, what's the imaginary part of this number? It's going to be cosine of the first times sine of the second, plus cosine of the second times sine of the first. Right? Right. And so you recognize, so you say, okay, look, that tells me that cosine of a sum is that, right? So you see that cosine of theta 1 plus theta 2, the real part of this must be the real part of that, right? Because they're the same thing. Right? So the real parts are equal. Right? And the imaginary parts are equal, right? So cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. Right? In other words, the addition formula for sine and cosine are not anything complicated. What they are is that the exponential function has this property. Right? E to the a plus b is e to the a, e to the b. Right? That's what this is. And actually, a lot of other formula can be derived in the same manner. I have a few more, but I'm not gonna. We don't have time to talk about that. Okay. Let me just say one last thing, which is really cool. If we try to, remember the logarithm, our expansion for the logarithm only worked in this interval here, right? Only worked in this disk. What's possible to do is to say, well, okay, so I can extend the logarithm to this disk. I'm trying to get it to the entire plane, right? All I've got is the extension to this disk, right? But I have the logarithm here at least, right? I have the logarithm here at this point. So I'm going to take a power series expansion around that point. Okay, and what happens is that you get that it's valid in this disk. Okay, you say, okay, well, I've got a logarithm on these two disks. And you say, okay, can I go further? Right, and so you say, okay, I'm going to take here, and that gives you this disk, and you keep on going around, and you can sort of bootstrap your way to the entire plane. But the funny thing happens, sort of a funny, maybe awful thing happens, which is that you go around. As you go around, you come back, and it turns out that when you come back, you get a different function. Okay, but we still consider that to be the logarithm. Okay, and you go around again, you actually get another function. It's related, but it's not exactly the same thing. You get another function, and as you keep on going around, you get different functions. And so the logarithm, in extended to the complex plane, is actually a sort of multiple valued function. Right, so it has an infinity of values, right? So you say that the logarithm has an infinity of values for each point. Okay. Now this is the part that would be kind of fun. The square root function, same thing. Okay. You try to extend it, and again you run into trouble, right? But you walk around, you come back here, and what do you get? So maybe you started off with your original square root function, you come back here, and you get the other square root function, Okay, so the square root function is actually, in the complex world, is one function. Okay, it's one double-valued function that where you walk around this world, you walk around the origin, you come back, you have this different function, you walk around again, you don't get a different function, you actually return to the original. Okay, you actually return to the original function. Okay, and this is actually, to end the course with something really cool, this is actually the idea behind Alice in the Looking Glass, right? The author, Lewis Carroll, was a mathematician, right? And so he has this idea, like, okay, let's tell a story where there's this place you cross over and you end up in the world where everything is backwards, right? You end up in the world where everything's backwards. You cross back through that thing again, and you end up in your normal world. Okay, and so like, you know, that's the idea behind Alice in the Looking Glass and its long-term descendant, the Matrix, right? You know, in the Matrix, right? When Neo enters the real world, he's in the imaginary world, right? How does he get to the real world the first time? He touches this mirror, right? The mirror flows over him, and he ends up in the real world, right? Right, so that's that. And so, you know, when the Matrix 2 was coming out, you know, the mathematicians are thinking, so is this the square root function or is this the logarithm function? Right? Like, are there going to be multiple worlds, an infinity of worlds, right? Or is this just going to be, you know, two worlds? Right?
You're talking about like walking around.
Yeah.
Can you go backwards?
Yeah, you can go backwards. So if you went backwards, you just come back to you get back to what you started. Yeah. But the thing is that there's something called a branch point, and as you go around it, my gosh, if you go around it, then you end up with the different function. Okay, so that's it for the course. Thank you for a fun year. I've enjoyed it myself a lot. I hope you've enjoyed it as much as I have.